Hello, the class. This is Dr. E again. Now we're going to cover a chapter on quantum mechanics. I think you're going to find this interesting. Things get really strange in the field of quantum mechanics. The big ideas that you need to know, or that you will learn, is that energy comes in discrete amounts, discrete packages. Also, you can't measure anything without changing it. Those are the big ideas. Now, when you talk to your mom and dad next time and they ask you, what are you learning in your science class, you just tell them quantum mechanics and don't worry about it, I've got it handled. But seriously, as Niels Bohr said, a Danish physicist, anyone who is not shocked by quantum theory has not understood it. And also Dr. Richard Feynman, who said that nobody understands quantum theory. So we're going to give you the high points, the tops of the trees in the subject of quantum mechanics. Quantum mechanics deals with the study of particles at the atomic and subatomic level. That is, things that are really, really, really small and moving very fast, like photons and electrons. Now, there are three revolutionary ideas that led to the field of quantum mechanics, and those ideas are, first, that energy is quantized or come in specific packages. Secondly, light can act like a particle, and conversely, particles or matter can act like a wave. These ideas, as we'll see, lead to what is called the wave-particle duality. That is, light can act like a particle sometimes. We thought light was a wave. And also particles or matter can act like waves. The particle-wave duality. It also leads to the notion that at this very, very nanoscopic scale, things are fuzzy, yet at the same time somehow discrete. Well, let's explore these three revolutionary ideas a little more. And first, let's talk about Max Planck, a German physicist, who first proposed that energy levels can be quantized. Now, what I mean by quantized, it's more like the steps on the right. That is, that energy occurs in certain packages of whole numbers. That is, 1, 2, 3, 4 packages of energy. Whereas up to that time, people had thought, if they had thought about this, that energy was more like a continuum, that it was more like the slope shown on the left. But Max Planck came up with this revolutionary notion that energy is quantized. That's the quantum in quantum mechanics. Albert Einstein then came along and he suggested from some experiments he was doing. Remember, Albert Einstein started out as a clerk in a patent office. And he did an experiment to show that light could act like a stream of particles. And so we can refer to light as acting like its small energy packets called photons, almost like they're small particles, yet we will see that they're massless particles. I know, it's kind of strange. Another important scientist was Louis de Broglie, who suggested that all matter that was moving, that had momentum, that means momentum is mass times velocity, so matter that is moving could actually act as a wave. That even you and I can act like we are waves, but our wavelength is so small that it's insignificant. But the point is that when you get to very, very small nanoscopic particles, that their wave character becomes much more significant. So on our scale, we don't really behave as if we're a wave. We behave as if we're matter, particles behaving classical physics, classical mechanics. But on a very, very small scale, things get really fuzzy and they start acting both like waves and particles. Let's explore this a little more, this wave-particle duality. We just said that photons appear to behave as waves and as massless particles. What do we mean when we say something acts like a wave, when we say light acts as a wave? Well, we've already covered waves and light. And one of the things it means is that waves demonstrate constructive and destructive interference. And this is illustrated in the experiment on the left, where we have a light source, a light bulb, shining light, and we have a barrier with two slits, two very narrow slits. The way a wave behaves, light being a wave, is that light will go through these slits and then it will fan out through both slits and it will produce an interference pattern. That is, there will be places where the waves constructively add together and also places where they will interfere with each other, so that the resulting pattern on the wall will show bands of light and dark, light and dark, light and dark. This is characteristic of a wave phenomenon. Light demonstrates this wave phenomenon, okay? But experiments were done to show that electrons also can produce this interference pattern. Electrons had been thought, and they still are thought, to be very, very small particles. They have a certain mass. It's a very small mass, but they seem to be particles. And the experiment on the right shows that they can also produce an interference pattern when a beam of electrons shot by what we call an electron gun is passed through a double slit, a barrier that has a double slit. On the other side, there will be developed a pattern, an interference pattern of dark and light and dark and light. This type of interference pattern would not be produced if the electrons were acting just as particles. They would only go through the left and the right slit, and they wouldn't demonstrate this wave property of interference patterns. But yet that's what is observed. It's been observed many times. So the point is that electrons were behaving like waves, yet we also think they're particles. Another important scientist and another concept is Werner Heisenberg and what is called the Heisenberg uncertainty principle. And this uncertainty principle is oftentimes represented by the equation shown. Delta x times delta p is greater than some number, h bar divided by 2. Delta x is the uncertainty in knowing the position of a small particle, that is, where it is. And delta p is the uncertainty in knowing the momentum of that small particle. Momentum, again, being mass times velocity. So essentially this says that for very, very small particles, we can't really tell simultaneously where they are and how fast they're moving, because the product of the two is greater than some very small number called h bar over 2. The significance of the uncertainty principle is that for these very small and fast-moving particles, like electrons, photons, that we can't simultaneously tell where they are and how fast they're moving. And it also means that the very act of trying to measure the position or the velocity of a very small particle alters these properties. That is, if we try to locate where it is, we alter its velocity. If we try to determine its velocity, we alter where it is. Now, for us, on a large scale, that doesn't seem to make a lot of sense. But when we're talking about these very, very small and fast-moving particles, this is what applies. And you've probably seen numerous jokes about the Heisenberg uncertainty principle, such as Heisenberg may have slept here. Now let's step back and compare Newtonian classical mechanics, classical physics, with quantum mechanics. Classical mechanics, on the left, the box on the left, works for large objects like you and I. It enables us to define the precise trajectory, and that is position and time, for any object as it is moving. It allows for a continuum of energies for an object, but it fails for very small particles, atoms, electrons, and photons. Quantum mechanics, on the other hand, picks up where the classical mechanics leaves off or fails to describe things very well. Quantum mechanics works best for very, very small objects. Quantum mechanics does not describe things in terms of precise trajectories, but only in terms of probabilities of position and energy levels. When we talk about the atom, we'll talk about the probability of electrons existing in certain orbitals, for example. In quantum mechanics, the energy levels are quantized, and it works for large objects like us, but quantum mechanics isn't necessary at all to understand objects like us and bowling balls and planets and things like that. So why do we study quantum mechanics? Well, quantum mechanics has led to our understanding of the positions of electrons and atoms in terms of what are called wave functions, which are the probabilities of an electron existing or being in certain regions of space and certain energy levels around the nucleus of atoms. So basically, we need quantum mechanics to understand atoms. There are a couple of other puzzlements about quantum theory, quantum mechanics that I want to mention to you, and you may have heard of some of these. One is the Schrodinger cat paradox. Now, Erwin Schrodinger was another one of these physicists who studied quantum mechanics. And he had this interesting thought problem about a cat. Now, it's not quite certain whether or not he liked cats or not, but his thought problem involved placing a cat in a box, such that in the box there was also something that a vial would break and it would poison the cat. And the probability of that vial breaking at any time was like 50-50, that it would either break or not. And so Schrodinger's thought problem is, well, if I place the cat in the box, how will I know whether it is dead or alive unless I open the box? And so his thought was that, well, the cat is both dead and alive until I interrogate, until I peek. Okay, so we'll see a video in a second that will illustrate this. And another interesting concept in quantum theory is what is called quantum entanglement, where the idea, and it's a strange idea, but let me try to explain it to you, that the notion is that there can be small particles like electrons that are paired in some way. And if you determine something about one of these electrons, you then will determine something about the other electron. And usually this is referred to in terms of the spin of the electron. If we can determine the spin of one electron, we can determine the spin of another electron because their fates are entangled. One would spin one way and the other way. And what is interesting about this is that if they are entangled in this way, they aren't necessarily close together. They can be very far apart. And the question then is, how do they communicate over large distances? So it's kind of one of these puzzlements of quantum mechanics. Okay, we'll stop now. We'll have a little quiz. Then you'll see a couple of videos that sort of illustrate some of these puzzlements. Okay, see you.